Welcome to my video course on Communications-Based Train Control, or CBTC for short. Today, we're unlocking the hidden technology that safely maximizes track capacity on your local metro system. We've got 5 main topics on the agenda today. First, we'll look at the fixed block problem. Then, we'll dive into the moving block solution. Check out the anatomy of CBT subsystems, talk about automating the train, and finally, touch on securing the railway. Let's get right into it.
Section 1. The fixed block problem. To really understand CBTC, we first need to look at traditional train control and the old-school way trains are kept apart to prevent catastrophic collisions. For decades, railways have basically relied on what we call absolute or automatic block systems. Think of this like a giant, rigid traffic light system. The tracks are carved up into fixed lengths, and only one train is allowed to occupy a block at any given time. Now, while this is incredibly safe, you end up with massive amounts of completely unutilized, empty space between trains. And hey, if you've ever been stuck waiting on a completely packed platform during rush hour, you know exactly why that's a huge bottleneck.
Because this fixed method leaves so much empty track, engineers were left with a massive puzzle. How on earth do we safely bring trains closer together? As our cities explode in population, we literally have to increase hourly passenger capacity. And doing that without spending billions to bore new tunnels or lay down entirely new physical tracks, that's the real challenge.
Which brings us to Section 2, the moving block solution. The answer to our capacity problem lies in a total paradigm shift, moving away from static physical track sections and moving toward continuous, moving safety zones.
To grasp this shift, take a look at how a conventional system works. It relies on a static speed profile. It rigidly enforces speed restrictions over unchanging physical sections of track, leading up to a fixed danger point. Because of this, the train always has to assume the absolute worst-case braking scenario based on those fixed physical markers. It's safe, sure, but it wastes a ton of valuable time and space.
But with CBTC, we get a dynamic speed profile. The system is constantly crunching the numbers in real time to calculate safe braking curves. It effectively moves the safety authority right along with the train. You can kind of think of it like adaptive cruise control on the highway. It lets trains safely ride much closer together simply because the safety buffer adapts continuously to the train's actual speed and exact location.
Section 3. Anatomy of CBT subsystems. So, to actually make these moving blocks a reality, and to pinpoint train locations without relying on clunky old track circuits, the system needs a continuous, high-resolution telecommunications loop.
According to the IEEE 1474 standard, a true CBTC architecture requires 4 major interacting subsystems. We're talking automatic train supervision, wayside equipment, train-borne equipment, and the data communication equipment itself. Now, designing all this requires strict adherence to some heavy-duty international safety frameworks. You'll see the rigorous application of the IEEE 6290 standard for overarching system requirements alongside EN 5126, EN 5128, and EN 5129. I know that sounds like a lot of alphabet soup, but these aren't just bureaucratic red tape. They are essentially the digital seat belts guaranteeing the absolute reliability and stringent safety of both the software and the hardware.
You can see how this all connects right here. Through continuous two-way data flows between the train's onboard antennas, trackside Wi-Fi access points, and central zone controllers, the train basically becomes a smart node on a network. It's constantly pinging its exact location and speed to the wayside equipment. The wayside equipment then instantly calculates and transmits back the train's safe limit of movement authority.
Section 4. Automating the train. We have the data flowing, but how do these digital communications actually translate into controlling the physical movement and safety of a massive, heavy steel train?
Well, it all starts with the absolute most critical component, automatic train protection, or ATP. This is your fail-safe subsystem. It enforces speed limits and guarantees emergency braking. Literally, if a train exceeds its authorized speed, ATP takes over and triggers an irreversible emergency brake. Those EN 51028 and EN 5129 standards we mentioned just a minute ago, they are hyper-focused on making sure this specific software and hardware never, ever fail dangerously.
Right alongside the ATP is Automatic Train Operation, or ATO. The ATO essentially acts as your virtual driver. It handles the actual acceleration, the cruising, and the incredibly precise stopping at station platforms. It's the system making sure the train aligns perfectly with those platform screen doors, giving passengers a perfectly smooth ride every single time.
And overseeing this whole operation is Automatic Train Supervision, the ATS. Think of ATS as the central brain of the network. It regulates the overall schedules, the routing, and the headways, or the distance between all the trains. It manages the big picture so that the individual trains can execute their specific routes without causing giant network bottlenecks.
If you step into an operations control center, you'll see human operators using massive ATS displays to monitor the entire network. Through the ATS, these operators can adjust dwell times at stations down to the exact second. For example, they can hold a train slightly longer at a platform just to ensure it merges seamlessly into a busy corridor without causing cascading delays down the line. By combining these highly precise subsystems, and again, guided by that IEC 6222090 standard, CBTC enables various grades of automation. This scales all the way from a manually driven train that just has ATP protection all the way up to GOA 4. GOA 4 is fully unattended, completely driverless train operation. We're talking about a system where even the door operations and emergency responses are handled entirely by the computer. Finally, Section 5, Securing the Railway. Because modern systems rely so heavily on wireless data networks to operate, we really have to address the critical IT complications that this level of connectivity introduces.
Here's the reality. Over 95% of radio-based CBTC implementations utilize Wi-Fi and Ethernet networks. Because of this, railways face very real cybersecurity vulnerabilities. When you move away from closed physical track circuits and move toward IP-based wireless networks, you inherently introduce the risk of unauthorized external access. And obviously, a breach like that could severely impact operations. So, to prevent hackers from causing chaos, transit networks segment their IT infrastructure using what's called the Purdue model. This strictly isolates the physical trackside sensors at level 0 all the way away from the central business logic up at level 3. In plain English, this means a breach in a station's public Wi-Fi or even a corporate email server has absolutely no direct digital pathway to the vital zone controllers managing train movements.
Furthermore, cybersecurity standards dictate a strict principle of least privilege. This just means that users, devices, and maintenance proxies are only granted the specific access rights absolutely necessary to perform their immediate tasks. It effectively limits the blast radius if an account ever does get compromised.
This whole philosophy creates a defense-in-depth strategy. By utilizing multiple firewalls, intrusion detection systems, and segmented zones, transit authorities ensure that even if a corporate IT network is somehow compromised, the operational technology, the actual physical train signaling, remains entirely shielded and perfectly safe.
As we push toward completely driverless, hyper-connected transit networks, we really have to ask ourselves, how will evolving cybersecurity standards continue to stay one step ahead of the digital threats targeting our cities? It is a truly fascinating engineering frontier. Thanks, we can see you in next video.